Our next topic is radioactive decay, or natural radioactivity, radioactivity that's occurring spontaneously in nature. Radioactive decay is a process by which an unstable atom or nucleus undergoes a whole bunch of nuclear reactions that ultimately produces a stable atom. So radioactive decay is a series of nuclear reactions that convert an radioactive, unstable atom to a stable atom. The radioactive decay is pretty well understood for a lot of elements. And in your textbook, figure 20.2, we have what is called the decay series for a particular radioactive element, uranium-238. So if we look at this decay series, if I can get it all the way up at the very top, starting way up at the very top, we have uranium-238. And you can see in the first step, so what this is saying is that in the first step, it converts to thorium-234, and it does that by loss of an alpha particle. And then the thorium converts to Pa-234, and it does that by loss of a beta particle, and on and on and on. At some points in the radioactive decay series, like when it gets down to this particular spot, it has a couple options. It can either undergo alpha or beta decay to give two different options. The next step is the opposite, another alpha or beta decay, so it comes together to make the same product. But this process continues down until you get ultimately the stable product of this reaction, which is a lead atom, way down here at the bottom. Each one of these steps, as you've probably noticed, has a time associated with it. The time that's associated with it is the half-life for each step. So throughout this process, especially the first step, some of these half-lives are really, really long, and some of them take place really fast, and that's pretty typical for a radioactive decay series. In general, our radioactive decay undergoes first-order kinetics. So this follows first-order kinetics. And because we know it's following first-order kinetics, we know that the half-lives come from the equation T1/2 equals 0.693 over the rate constant K. That's the half-life for a first-order reaction. So knowing that our half-lives are going to follow this equation, we can measure the half-life of a radioactive substance, and we can use that to figure out its rate constant K. And then we also know that concentrations are going to follow first-order kinetics as well. So all concentrations are going to follow our equation. The natural log of the concentration at time t is going to be equal to the negative rate constant times that time plus the natural log of our starting concentration. And for radioactive reactions, it's useful to actually use this equation in a little bit different form. So we're going to go natural log of A at time t minus natural log of A at time 0 equals negative KT. And using the properties of logs, we're going to change that to the natural log of A at time t divided by A at time 0 equals negative KT. And a lot of times with these radioactive reactions, we're not actually dealing with solutions, so concentrations doesn't make a lot of sense. But we can instead choose to express this just in terms of the number of atoms. So we're going to change that AT over A0, we're going to change that to N1 over N0. And let me define that over here. We're going to say N1 is going to be simply the number of our nuclei or our atoms at time t, whatever that time is. And N0 is going to be our initial number. And if you're wondering how we could make that jump, like how could we just ignore molarity completely and just jump straight to a count of atoms? Well, let's kind of think about what we're saying over here. When we're saying concentration of A at time t over concentration of A initial, we are saying the moles per liter at time t over the moles per liter at time 0. And the liters are going to be a constant in this. The volume is going to be a constant. So this equation really is simplified to the moles at time t over the moles at time 0. And mole is just another way of counting. So if we can say mole over mole, we can definitely say the number of nuclei over the number of nuclei. So carbon dating is an application of this radioactive decay. Carbon dating is based off of the radioactivity of the carbon-14 atom. It is based on the radioactive decay of carbon-14. Carbon-14 undergoes radioactive decay to produce nitrogen-14, and it does that by spitting out an electron or a beta particle. And so we can use the amount of carbon-14 in a particular substance to make a prediction about how old the substance is. Here's an example of how we would do that. If we have a piece of freshly cut wood, the carbon-14 activity for this particular piece of wood, and it's going to depend on the type of wood. The carbon-14 activity is equal to 15.2 disintegrations, as in like falling apart, disintegrations per second. So let's say that we have an artifact of the same type of wood, and we measure its carbon-14 activity. And its carbon-14 activity is 9.1 disintegrations per second. The half-life of carbon-14 is 5,715 years. Can we calculate how old this artifact is? Before we jump into this math, let's think about like what's actually going on here. I'm gonna draw a tree. So when this tree is alive and it's doing its photosynthesis, which you guys know what that means, it is exchanging molecules with the environment, as you know, and that includes bringing in carbon-12 as well as carbon-14. So as it is absorbing CO2 from the environment, it's bringing in carbon-12, and carbon-14, and we also have carbon-13 as well in the mix. And those carbon atoms are being integrated into the tree as part of the structure of the tree, coming in and out. And so as long as this tree is still alive and it's still quote unquote breathing and absorbing these materials, the amount of carbon-14 in the tree, the percentage of carbon-14 relative to all carbon, is consistent with the percentage of carbon-14 in the universe. So let's say if this particular tree is 99% carbon-12, that's going to be the same as how much carbon-12 is in our atmosphere. Once the tree dies or a piece of wood is chopped off of the tree and it's no longer alive and no longer exchanging carbon with the environment, it can't bring any new carbon-14 in. The carbon-14 is only decaying. It's just going away. The concentration is getting smaller and smaller and smaller. So we can compare the amount of carbon-14 in a piece of dead wood relative to the amount of carbon-14 in the atmosphere. We can use that to make some guesses about how long ago it was when the substance died. So the way that we're going to solve a problem like this, we're going to need to use both of our kinetics equations. So we're going to need to use the natural log of the amount of substances at time initial and time t, and that's going to be equal to our negative rate constant times time t. What we're trying to solve for in this equation is right here. How old is the tree? We're trying to figure out time t. We don't know the rate constant for this tree. We know the carbon-14 disintegrations, that's going to give us N1 and N0, but we don't know the rate constant. So our first job is to figure out the rate constant, and we're going to do that using the half-life. We know that the half-life is 0.693 over the rate constant K, and so that means that we know the half-life times K is equal to 0.693. That's just rearranging that equation. And we then know that the rate constant K is going to be 0.693 divided by the half-life, T1 half. We know the half-life, so we can plug that in and solve this problem. The half-life is 5715 years. So the rate constant for this guy is 0.693 divided by 5715. 1.21 times 10 to the minus 4 inverse years. So now that we know K, let's bring back this natural log equation. N1 over N0 equals negative KT. Again, T is what we're trying to figure out. We know the value of the rate constant, so we've got that. And the way that we're going to measure N1 and N0 is with the disintegrations or the activity. So we know at initial, so N0, that would be immediately after it died, a freshly cut piece of wood, 15.2. And then N1, that's at this time that we're trying to figure out, 9.1 is the disintegrations for our current artifact. So we're going to plug in 9.1 for N1 and 15.2 for N initial. Our rate constant, which is 1.21 times 10 to the minus 4 inverse years, and solve for time t. 9.1 divided by 15.2, take the natural log of that. We get negative 0.513, and that is equal to 1.21 times 10 to the minus 4. And now we're just solving for time t. I think I lost my negative sign. There's my negative, bring my negative sign back. So this time is 4,240-ish years. That is the age of this artifact.